Hi, everyone. Welcome to PARC Forum. Thank you very much for coming today. My name is Mike Kunyavsky. I am a principal in PARC's Innovation Services Group. Today we're very happy to welcome Ade Mabogunje to talk about design thinking and his research in this over quite a long period. I'm a professional, or a self-defined professional user experience designer, as I have been for the last 20 years. And for me, one of the most interesting things about design during the period that I've been a professional designer is that initially, when I started, design was very much a kind of a front-end thing. It was a thing that came out of graphic design or industrial design, where it was really an outgrowth of the arts, and it was a kind of final step in an industrial production process. Over the 20 years that I've been doing this, the practice and my work has essentially progressed further and further up the food chain until designers have now become concerned with engineering questions or with product direction or with business models. And so it's become a very interesting discipline in that the core activity touches virtually every aspect of technology development. And it's become such a big part of Silicon Valley technology development that the large technology companies, Google, Facebook, Amazon, are swallowing up whole design studios in order to be able to get access to design talent. Whereas it used to be this kind of thing that was a kind of a freelance activity that you used to do as a contract at the very end of a practice. Now it's become essentially something where the designers sit at the table and they become part of the process long before the first line of code is written. And they're often the last people to touch the product before it goes live or before it's shipped, which is a really deep fundamental change that has actually created some challenges in terms of defining what design is. So if it's now part of nearly every aspect of creating a product, well, what is it? Where does it stop? What is now not design? And so in our conversation, what's very interesting is that it is now not really a materials-based practice anymore, or a tools-based practice. It is a process and a way of thinking about the way that things are created, in which case it becomes the kind of a parallel to engineering or science or art. And that, I think, is a very novel and interesting phenomenon that is quite recent and which Ade Mabogunje has been studying for a very long time. And with that, I would like to welcome him to tell us more about his research. So, thank you.
Okay. Thank you very much, Mike, for that introduction. Welcome, everyone. And what I'd like to do today is to engage with you a conversation about design. And like Mike said, there's been a lot of variations in the field. And in talking about design and also talking about engineering, what I want to share with you is some of what we've been doing in our research and hopefully also engage you. But for that, I want to at least get a sense of who the audience are. So I have a few questions to ask everyone. So I'm going to go down a list, and I just want to know how you think of yourself. Let's see. OK. Something happened with my list. But if you feel the first number is designer, if you feel you're a designer, please raise up your hands. OK. If you're an engineer, a scientist, okay, an artist, okay, an educator. You folks are multiplexing, huh? An investor, okay, an entrepreneur, How many jobs do you people have? Okay, other professionals at least. Oh, okay. Managers and administrators. Okay, and last question. How many of you are attending the Global Innovation Summit? Okay, thank you.
Let's have the most important category.
What's that?
Developer.
Oh, thank you. Developers. Okay. Let me caution you. Some housekeeping. The work I'm going to present is still work in progress. So think of it as a construction site. There's a lot of material to be covered because of the nature of design. It's so diverse. But as we're seeing, as Mike mentioned, in becoming a fundamental discipline, there requires for us to understand each other and begin to sew the seams together. So that's, if you see the breadth of material, it's just to make sure that all the disciplines that are concerned about design, they at least understand that we're talking about the same thing. And so you should seek coherence rather than rationality, because within each of the fields, each of the disciplines, they have a structured way of looking at design. But as a group, as a collective, it's the coherence between all the different disciplines that begins to make design work as a fundamental science. I tend to use PowerPoint slides because sometimes, very often, I do have foreign audience, and they say they can follow things better that way. But it's going to show about 4 videos. The videos will be the main things, and the PowerPoint slide is just for people to follow the conversation. Now, my research has a very local focus. I'm going to talk about Stanford, IDEO, Xerox, Silicon Valley, the US. Why? Because design is context dependent. And that's very important, because sometimes I was in New York about 2 years ago, and I said, well, what we're trying to do is to create something like Silicon Valley in New York. And they were very upset with me that, no, New York, we don't want to be like Silicon Valley. But I've been invited there because I think there was some session by Mayor Bloomberg. I said, well, why are we here? So I think people get a bit territorial. So I want to make sure, then also if I say Stanford, then say, hey, I'm from Berkeley, what's the point? Okay. Okay, so I will use these as prototypes. They're prototypes, but because of the contextual nature of design, it's difficult to just pick things from different places and not cohere them. So that's very important why I use these examples, because there's a sequence through them. Finally, one of the things I want to mention is that the Silicon Valley is to the knowledge revolution what the first steam engine was to the Industrial Revolution. Now, that's a very important part, because as you'll see later, if we're able to understand, because I assume there are like 50% of engineers here, once we understood that it took just 0.5% of carbon in iron to make steel, then you could replicate the process. So if we understand some of the things that makes the Silicon Valley work, then it can be replicated, and it's a design phenomena in a sense. So that's where I'm going, and once we understand the Silicon Valley in that way, there are a lot of opportunities that begins to open up. Okay, do you get the flow that we're going to? Okay. This work has been sponsored by several people, so I'll just mention some of them. Very early on, we had a project with NASA, which was trying to conserve design knowledge to allow the younger astronauts to access some of that knowledge. The Digital Libraries initiative has been key, because once you conserve the knowledge, how do you store it? Then we began to explore what are some of the global implications of the understanding of design. So the Kosmetsky Global Collaboratory at Stanford. Is Sharik here? Sharik is the executive director. He's been very instrumental in this work. Thank you for coming. Yeah. Then we did a project, a pilot in Nigeria and in India, and those are some of the sponsors. And then the Hasso-Plattner Design Thinking Research Program, both here in the US and in Germany, has been also part of the sponsors. I have a long list of, and I should mention, the work I'm reporting here is not just my own effort. It's a there's just been a lot of people who have worked on it, and some of you may be familiar with some of these people. Very early on in Stanford, I worked with, when he spent some time in Stanford, Doug Engelbart, and part of this pursuit is a continuation of that work. But I put up this list because it's just been a lot of people involved, and I cannot take credit. All the mistakes are mine. Okay, so here's the outline of what I'm going to talk about. What is design? Can it be improved? Can it be scientifically understood? Because once we are able to do that, then other things will be possible. And then the last question, so what? Okay, so let's start the first question. What is design? These are really two questions. And what's the relationship to engineering? So I have another poll for you. Look at these 5 Venn diagrams, and I just want to know what people think of the relationship between design and engineering. Can you all see them? Oh, sorry. Okay. Let me see what I can do. Are you ready? I'll move them up. Okay. Okay. Okay, can you all see them? Okay. Rapid prototyping, yeah. Okay, you've made your vote. Those of you that think the relationship between design and engineering is A, can you put up your hands? Okay. B. Okay. C. Okay, D. Aha, interesting. E. Oh, no E. Now, that's interesting. I'm shocked. One of the reasons why we tend to use the word design thinking is that a lot of artists feel they own design. So they get very upset with us. So they said design is ours, not engineering. So if there's an artist here, he'll have told you that's the difference. Okay, so I will, you can see the variation that everybody is having a different, we had people vote in at least A, B, C, D. What is the relationship between design and engineering? One of the very, very useful ways by which we can in fact show it has been the deep dive video that was recorded for IDEO. And I'll show a segment of that just for those people that are not familiar with it.
Day one, and these people have a deadline to meet.
So welcome to the kickoff of the shopping cart project.
This is Palo Alto, California, in the heart of Silicon Valley, and these are designers at IDEO, probably the most influential product development firm in the world. IDEO has designed everything from high-tech medical equipment to the 25-foot mechanical whale in the movie Free Willy and the first computer mouse for Apple. Smith ski goggles, Nike sunglasses, NEC computer screens. Hundreds of products we take for granted.
The point is that we're not actually experts at any given area. You know, we're kind of experts on the process of how you design stuff. So we don't care if you give us a toothbrush, a toothpaste tube, a tractor, a space shuttle, you know, a chair. It's all the same to us. We want to figure out how to innovate by using our process, applying it.
Project leader is Peter Skillman, a 35-year-old Stanford engineer. Project leader because he's good with groups, not because of seniority. He's only been at IDEO for 6 years. The rest of the team is eclectic, but that's typical here. Whitney Mortimer, Harvard MBA. Peter Coughlin, linguist. Tom Kelly, Dave's brother, marketing expert. Jane Fulton-Suri, psychologist. Alex Kazaks, 26, a biology major, who's turned down medical school 3 times because he's having too much fun at IDEO. Safety emerges early as an important issue.
Okay. So there are a few things I will point out there because that will frame what we've been talking about. you can see there's a focus on the customer. So we've used the term human-centered design. Second, Dave said it's about the process. So it's about the process of design. And then you can see the diversity of the team. Most engineering teams tend to be multidisciplinary. Also the liveliness of the place, not always what we do in engineering. And finally, that the leader of the group is somebody that is good with groups, not because of his seniority. So these are some of the features we begin to see in design. And in the next slide, which will be the longest slide you'll read, one of the people who has been quite a pioneer in that field has been Herbert Simon. And he, in his Sciences of the Artificial, gave quite an interesting definition of design, which I'll share with you. You'll have to do some reading, but I promise you that'll be probably the last one. Can you, oh, you can't see. Now I can't engineer that. Let me try. It's, okay, let me see what, I'll read it, okay? Historically and traditionally, it has been the task of science disciplines to teach about natural things, how they are and how they work. It has been the task of engineering schools to teach about artificial things, how to make artifacts that have desired properties and how to design. Engineers are not the only professional designers. Everyone designs who devises courses of actions aimed at changing existing situations into preferred ones. The intellectual activity that produces material artifacts is no different, fundamentally, from the one that prescribes remedies for a sick patient, or one that devises a new sales plan for a company, or a social welfare policy for a state. Design, so construed, is the core of all professional training. It is the principal mark that distinguishes the professions from the sciences. What Simon was arguing is that as human beings, we did not design the sun or the moon or the stars. But every other thing that we have with us has been the product of our own intellect as humans. We design products, we design organizations, we design religions, we design families. That variety is the product of our consciousness as humans, and that if we can find a way to get at design, we will be able to steer ourselves in new and different directions. So that's a very core part. Now, I'll just answer a few questions. Why bother about design? The first thing we know is that design is critical for economic growth. Robert Solow, in 1962, as an economist, said he was able to show mathematically that fostering innovation was key to economic growth. But at that time, they did not know how to get innovation. In the last, let's say, 2 decades, we're beginning to see that design is directly coupled to innovation. So if we can understand how design works, then we will be able to get more precision in our innovation processes. So that understanding design becomes very key to economic growth. And if we have this growth, what are some of the challenges that we could be up to? Most of you have seen a lot of riots over the world, a lot of youth unemployment. Silicon Valley happens to employ a lot of its youth, so lots of governments are quite interested in understanding what we're doing differently. But there are also opportunities. We have design in healthcare, in defense, in the media industry, but we also have challenges. When you see what's happening in Syria now and the displacement, the orphans and the widows, all in the refugee camps, the natural disasters we face, poverty, aging and disability. These are all challenges that we can begin to see that when we look at them from a design perspective, we could begin to find new solutions to them. So not only in terms of building the different artifacts for work, but these are challenges that often one doesn't think of that we can do it by design, but they are problems that we have created as humans, and the same intellectual capability can be used in terms of working towards a solution that improves and changes the situation. Okay, so that's part of, I've sort of defined what design is and some of the why of investigating design. Can it be improved? I'll point at 3 of the early works that I thought were quite commendable, and then some of the challenges. So the questions we often then ask is, what are designers really doing? And how can we improve the performance? And of course, there's a list now coming up, which I will have to explain it to you. Sorry about the, so the existing lines of work. How many of you are familiar with Doug Engelbart? Okay, so one of the things that Doug was looking at was that he had this notion that the problems in the world were growing at this rate, and our ability to cope with them was growing at this rate. So he asked the question, can we use other parts of our bodies to solve the problems? That if we're just limited to looking at problems with our eyes, then we might be too slow in finding solutions. So part of getting to the mouse was that can we use the mouse for solving a problem? They also, at that time, developed the concept of the windows, because he said, as humans, when we hear a noise outside, we can easily shift our attention and, within the window frame, understand what's happening there. He also said, when we talk to each other, and I say, well, I was in Paris last week, our minds could jump to Paris if we've been there before. That's the hyperlink that we now see in the World Wide Web. So in terms of Doug's approach, it was saying, can we augment what humans are already doing with new tools? In Carnegie Mellon, there was Herbert Simon, and they were looking at, can we automate design? Can we use artificial intelligence to replace the designer? And that was another approach, because these are all different approaches to improve design. Then there was another group here at Xerox PARC and also at Institute for Research in Learning that was looking at the social and human aspects of design. They came up with concepts like situated cognition, situated learning. I think Bill Clancy is here from IIL, situated cognition. And so these different approaches were all looking at how do we wrap our hands around design. There were a few limitations to these studies. First was engineering is a very, very broad discipline, and it's practiced in a variety of industrial contexts. Second, nobody knew what performance really looked at. If you improved engineering, then what? What will it look like? And finally, there were no standard ways of measuring performance. In the basic sciences, we have 7 basic units that we use, and the rest are derived from these basic units. Mass, length, time, temperature, current, amount of substance, and light intensity. If I said, what are the metrics that we use to measure design performance? These ones we use to measure our vital statistics when you go to the hospital, our weight and our height. So we were quite interested in saying, well, how can we address this problem faced with these challenges? So we found a way to begin to overcome some of these challenges. And the first one, which was that engineering is quite a broad discipline. Compared to medicine, that medicine too is a broad discipline, but it all boils down to the human body. Engineering and design, by contrast, is just wide. Now, we were lucky that we had at Stanford an industry-sponsored design class that every year took in projects from a variety of industry. So we said, good, we'll use the class as a way to begin to understand what happens in design. That's what the class looks like. But we take in projects from a variety of industry. This way, we can see what's common in the processes in the different companies. Second, nobody knew what design performance looked like. Now, this was in the 80s and 90s, and luckily, something else happened at that time. How many of you remember what happened in the 80s and 90s with Japanese? In 15 years, the number of patents by Japan increased up to about 2,500, 1,000 more. The DARPA perceived this as a national security threat. And a number of signals were issued that we need to produce more engineers who can go after Japan. And several companies and researchers went out to study Japan. Amongst those were Kim Clark and Takahiro Fujimoto that studied for 5 years companies in Europe, the US, and in Japan to understand what were they doing differently. They came up with this chart, which was quite an interesting one. This is Japan, and they said, if we look at their different knowledge intensity, this side is, this is design and manufacturing. This is Europe and the US, and this is Japan. They were able to show that the level of knowledge, the patterns of communication had a direct impact on the lead time. Now, this was the first major study at scale that was showing communication patterns mattered. We had thought maybe the Japanese had a new mathematical equations or they had better computers. But this brought it back to human interaction. That with human interaction, there are a number of things you can do that will change the level of performance of companies. So this was really very, very important in our studies. So at least we had a vague idea because these knowledge levels are still a bit vague. What's that? But it gave us an indication of, okay, this is what performance could look like. The last thing, no standard ways of measuring design. So what we did was to create a laboratory at Stanford to study the classroom that we had brought in several projects. Can you see the last slide? OK. I'll change it again. So the laboratory studied the class, which studied industry. How many of you are familiar with Engelbert's bootstrap strategy? Oh, not many people. OK. Part of what Doug had in mind was that we could bootstrap ourselves into improving performance so that this could be bootstrapped to improving this, to improving the next level. But this was what we were now looking at, that the laboratory will study the class, which was able to bring in several facets of engineering into it. So the next question, can design be scientifically improved? We were trying to measure it, but what will it look like? Again, it's trying to get a sense of design. And can we measure it? Can we have mass or length? We were quite eager to see such a disparate process. OK. So in the next slide, I will try to share with you how we began to approach this problem of measurement of design. We adopted, and I'd like to give you some examples of these measures. So first, we adopted an engineering approach, feedback diagram. By the number of engineers here, I know they're all, how many of you are used to this feedback control diagram? Just by show of hands. Aha, OK. In design cycles, they'll use the word iteration, and engineers will use feedback control. But that's the basic mechanism that in engineering, we develop our projects through several iterations. What we did was to really come in as engineers and say, well, what if we replace the plant with humans? Instead of taking technical variables, let us take human variables in the design and begin to see how can those variables be used to improve performance. But engineers never work in a vacuum. And so we knew that we also had to take the environment variables, the context variables. As it happens, the context variables was what's the environment that we're working in. It so happens to have been in the Silicon Valley. So we paid attention to what's happening in the valley because we knew it will affect the engineers within our lab because they're interacting with the environment. Now, this diagram is very important to understand what we've done. It's not a study of the product. It's not a study of the consumer. It's a study of the producer, the people thinking about how they're going to meet the challenges. As engineers, we were studying ourselves. We were using our own methods, our feedback diagrams, to understand what we did. So it was reflective and reflexive. And we brought in several engineers because only they can tell us what's going on in their minds as they're solving problems. we looked at a lot of variables. I'll give you a sample of that here. Communication variables, how they're communicating, disposition variables, and institutional variables. Several of these variables, now the last set of variables, the institutional variables, are not variables that we looked at directly. We had partners that worked with us in looking at some of those institutional. But the disposition and communication variables were all part of what we looked at. I've arranged these variables, I've grouped them in 3 categories. I've borrowed here from the work of Albert Bandura. Albert Bandura, he had what he called a triadic model of reciprocal causation, which basically means that a person, his behavior, and the environment were linked together. Albert Bandura was also known for his work on self-efficacy. And part of what he was saying is that this is the environment that constrains our behavior. And once you understand that whole constraint, then ways of improving it or breaking out of it become very, very possible. So let me give you an idea of some of the things we were measuring. Gestures. This work was actually done here in Xerox PARC with John Tang worked with Lucy Suchman. They took a video camera and they followed engineers, I think at Webster's. There's a Xerox office in Webster's, is that correct? Yes, so they took the video and followed the engineers around, and what did they find? Engineers in the conceptual stages use about 35% gestures. Now, that should come as no surprise because what they're trying to invent does not exist. It doesn't have a name. So when you watch engineers or designers in that early stage, they're trying to communicate what doesn't yet have a regular name within the culture. The second was some of the work I had done. I looked at the engineering documents, and I extracted the noun phrases, the names they were given to documents. And we found that we could use that to track the progress of their work. Because as they create things, they have to name it in order to communicate it in a group. So one way of thinking of this work is to say, if I want to know all the things that have been invented since 1960, if I take the dictionary today and subtract the dictionary in 1960, I'll get a rough approximation of what we've invented. So for example, if in 1960 you have the mouse, it was a rodent in 1960. Now, if you type in mouse, you'll have 2 entries, the computer mouse or the rodent. So we can know that, in fact, these are the different things that engineers have created. The noun phrases will look something like this. They're quite simple. Steel friction disc, connecting links, rotating inner shaft. That's the language that they'll use. Now, you won't see a shift in language when we try to optimize, because it's going to be the same form. We've just changed the dimensions. But when we create something new, you'll see a new unique noun phrase that signals that something new has been created. Another of my colleagues, Ozgu Eriks, started looking at the questions that engineers are asking during design. Now, that's very important because in the management literature, they often do research on decision making. In engineering, we do research on question asking. Because this is what really you'll find a lot of the engineers doing. What Ozgu found out was that he could distinguish between 2 types of questions. What they call deep reasoning questions, which have true or false answers, and another set of questions that are called generative design questions. These are questions that generate new scenarios for people to work on. And he found that, in fact, for all the literature, very few focused on the generative design questions. Most schools teach critical thinking. Is it true or false? But there are these sort of questions that you'll find designers and engineers are asking that are generative in the way they come up. Ozgu found that it was only those teams for which they had people asking an equal number of both deep reasoning questions and generative design questions that had a very high performance. I'll move through the next slide. Okay, so the generative design questions are often what we use for our divergent process, and the deep reasoning questions are what we use to prune. And that's one of the things that Ozgu found out. But as we continued our study, one other thing emerged at Stanford. The class I spoke about has been running for about 40 years. Over that 40 years, we found that very few teams failed because of technical reason. When there was a failure, it was because the team members did not get along well. Because they had access to a lot of the professors on campus and the different students. So technical problems was always solved. But when a team cannot get along well, it was the end of a lot of the projects. So the next slide, one of our researchers, Malte Young, was very interested in what causes these teams to break up. And so he borrowed from the work of John Gottman. John Gottman does research on marital couples. He has studied in his lab about 2,000 married couples, and he was able to, he measured their breathing rate, their heartbeat, their galvanic skin response, which is their sweating rate. And when he brought them to their lab, to his lab, which is very similar to our lab, he is looking at also their facial expressions to understand their emotions. And he was able to see that when a couple engages in a pattern of conflict that has a negative gradient of emotion, it was highly predictive of divorce. Whereas if they could change that gradient to a positive gradient, then the marriage has a chance of success. So Malte took that work and said, can we use that to predict design teams? And what he was fascinated most with was that Gottman just needed 15 minutes of video to predict the performance of a team. So what Malte did was to try to replicate Gottman's study. We were able to look at engineering teams, and with 15 minutes of interaction, he was able to rank order the performance of the teams just by looking at their emotions. So that was quite critical. So we had these different variables we were looking at, and it was just, we started becoming overwhelmed by it. I put it here, so many variables, so little impact. We could analyze and describe design, but we were not able to intervene in any meaningful ways as engineers. This was very frustrating. So our challenge was, how do we integrate all these variables? E.O. Wilson, the biologist, had made a comment several years ago about the slow rate of progress in the social sciences. He was comparing social sciences to the medical sciences and said, in the medical sciences, they have a body of knowledge that is hierarchically organized, and it allows them to build up. Whereas in the social sciences, they all remain within their domain, and the language is not in any way unified. So the economists and the psychologists are not really talking to each other. And he said, that has limited the rate of growth in the social sciences. And when I looked at our own variable, I said, I hope we're not going down that route in which we have very disparate measurements. So we really were at a loss. How can we integrate these variables? And as engineers and designers, one of the things that we try to do is synthesis, that we could analyze in one phase and we could synthesize. So we were able to gain some inspiration. So rather than tell you about our inspiration, I will share with you the inspiration. Can we dim the lights, please? Mozart was our inspiration. Okay, so let's see what it's like.
Cannot afford to provoke our nobles or our people simply over a theater piece.
Majesty, this is just a frolic. It's a piece about love.
Love. Again.
And it's new. It's entirely new. It's so new that people will go mad for it. I have scenes. The end of the second act, for example. It starts out as a simple duet. Just a husband and a wife quarreling. Suddenly, the wife's scheming little maid comes in. It's a very funny situation. Duet turns into trio. Then the husband's valet comes in. He's plotting with the maid. Trio turns into quartet. Then a stupid old gardener comes in. Quartet becomes quintet. And so on and on and on. Sextet, septet, octet. How long do you think I can sustain that, Majesty?
I have no idea.
Guess. Guess, Your Majesty. Imagine the longest time that such a thing could be sustained and then double it.
Well, 6, 7 minutes. 8 minutes?
20, sire. 20 minutes. 20 minutes of continuous music, no recitatives. Sire, only opera can do this. In a play, if more than one person speaks at the same time, it's just noise. No one can understand a word. But with opera, with music, you can have 20 individuals all talking at the same time, and it's not noise, it's a perfect harmony.
Okay, please, lights on. With music, 20 people can talk at the same time, and it's a perfect harmony. Well, we have all these variables. What can we do with music and get all of them to synchronize? So, so we started looking at that. So this is our lab, and I will share with you part of the notation that we developed. I'll play it once, and I'll play it with the notation, and you begin to see what we did discover.
Could we create something that keeps them like
together?
Yeah, so that kids like during a car trip, they wouldn't get bored.
Then they could do something like Legos, but it. Well, anytime you're dealing with pieces, that's the problem.
Yeah.
So like you have to eliminate the whole premise of Lego to make it work.
But to have something like a nest, because it's so boring.
Design like a lab kit so you can play with your Legos?
Yeah, a lab,
okay.
What did you say? A lab kit.
Yeah, so.
And it could be a...
Okay, so I'm going to now replay that. It hung up partially, but I'll replay the next one, but you'll see it now with the notation system.
Could we create something that keeps them like
Together?
Yeah, so that kids like during a car trip, they wouldn't get bored.
Then they could do something like Legos, but it. Well, anytime you're dealing with pieces, that's the problem.
Yeah.
So like you have to eliminate the whole premise of Lego to make it work.
But to have something like a nest, because it's so boring.
Design like a lab kit so you can play with your Legos?
Yeah, a lab, what did you say? A lab kit.
Yeah, so...
And it could be a lab kid.
So you have your own personal lab kit, and this is your sandbox of Legos.
Let's use that.
Oh, a Lego sandbox.
Yeah, I think that's
Lego
great.
sandbox.
Okay. Now, this work draws on a field of study called cognitive narratology. It was developed, Mark Johnson and Lakoff had been looking at embodied cognition. So the notion that for most of us, if I asked, where does tomorrow lie relative to your body? Most people would say it's here. Now, tomorrow is just a word, but why is it in front? And so what you begin to see here is that the primitives is about I'm going somewhere. And when somebody has a block, when somebody says, no, you can't go, we actually feel they've just stopped us in our motion. In other words, our language evolves as a function of how we perceive our bodies moving in space. So let me give you an example of how this notation would work. Okay, so let's go for a walk. No, it's raining. We can take an umbrella. Now, that is an overcoming. You've been able to overcome something that was told to you. Now, let's look at another scenario. Let's go for a walk. No, it's raining. Okay, let's watch a movie instead. That's a deviation. And as you watch teams begin to interact, we begin to say now, in that motion, we can look at their interpersonal interaction. On top of that interaction, we can then also layer their ideas. The ideas here are marked in red. So we now begin to see that, in fact, the conversations that engineers are having and designers are having is what, out of that conversation, emerges the ideas. Okay, so when we then look at this conversation, we can begin to see that, in fact, the measurement of engineering design follows the whole pattern that we have been using. That engineers, when we had physics, we used mathematics for physics because that expressed what we knew about physics. When we had chemistry, we had a different notation because the interactions of them were very different. When we had the discipline of biology, we used the sequence. What I'm saying is that right now, in design mechanics, because it's in those interactions that design emerges, this begins to give us a way to manipulate the engineering function. In fact, based on this, we can now begin to say, let's try a different behavior. Or you are one that blocks people too often. We can extract the aggregate behavior of the different engineers. Furthermore, we can in fact see, sometimes which we've seen in our lab, two engineers that their interaction is just beautiful. Anytime they get together, you'll see good things emerge. And another set in which not a very good interaction, these folks are going to kill themselves. Okay, so these interactions now give us that, in fact, right under our nose, that language has been what we have used. It's artificial in itself, but with language, we're able to now change different representations in engineering. Okay, so this is what we're beginning to see, that in fact, design and the process by which we build our civilization hinges on the way we interact with each other. We see instances where sometimes some people, when they are blocked, they keep quiet. For them, being blocked is a bit shameful, and they shut down. And when you see that, then there are things you can do to intervene to help them because they can see themselves. So the language began to help us reflect on how we did engineering and design. So the last set of points I wanted to talk about is, so what? And I want to talk about two implications of that. One is the economic implication, and the other is the academic and the scientific implications. We go back to our diagrams, because what I just showed you now were just the variables inside the design, these human variables. But like I said, as engineers, we also operate within a larger context. And for us, that larger context is the Silicon Valley. As a lot of people come to the Valley and they said, oh, go to the Valley, they have technology parks and universities. But that's not what you can build technology parks and universities. It won't produce a Silicon Valley. It's the micro interactions, the behaviors that we have that produces the Silicon Valley. But we have to know, is the environment, how does that environment shape that behavior? So at this point, I'll stop here so that I can raise the institutional variables, because that's what I want to discuss. Because now that we know what the human processes are, I want to spend a bit of time looking at the environment, because those are important variables. Can you all see the last set of slides? Okay, I'm going to raise them up. Just do that in real time. Good. Okay, can you see that? You can? Okay. So the institutional variables, I already mentioned the work of Robert Solow. When you look at the institutional variables, there's something, when you look at the nature of leadership, you will see two things. It's about vision, but also the discipline. We have two very interesting work on looking at vision, part of the work that Sharik spearheaded, which was looking at the vision of leaders. But in terms of the rules, a recent work came out by Victor Huang and Greg Horowitz that was looking at some of the behavioral rules. In the feedback diagram, we also talk about what's the control laws that allows your feedback diagrams to work. So I'll share with you some of what these institutional variables will look like. It has also an element of capital because the investment is an important part of the feedback loop. And we were lucky here in the Valley that starting in the 60s, we had this whole phenomena of venture capitalists. And what that did was that it gave feedback to the inner loops to produce more. In a lot of other regions, they never allowed the engineers to see what the money was doing. So the feedback was impaired. They don't know what's working, what's not working. But the whole issue of stock options and capital was beginning to give engineers in the Valley feedback. And so let's look at some of that. I often trace some of my story through Engelbert's mouse, which, as you know, half of it was funded by, this first phase was funded by DARPA, and the next phase by venture capitalists, Apple and the commercialization. So we can already see that we have a two-cycle process in the Valley. Here's the government playing its part, and here's the venture capitalists playing the next part. There are 3 books that I want to recommend if you have to read any book, which will allow you to understand some of the institutional variables. It's these 3 books. This one is by Lucena, and he calls, the title is Defending the Nation. The second, The Mystery of Capital, and the third, The Rainforest. Here, we have more looking at the military-industrial complex. And with the publication of The Rainforest, it's really looking at civil society, how we can do almost the same thing, but having a more civil-industrial complex. And I recommend these 3 books to you. So let's look at vision. And that's a very important component. It's a variable that any leader has a vision. And so one of the people that has been quite influential in the Silicon Valley has been Frederick Terman, the former dean in the School of Engineering at Stanford. What was his vision for Stanford as a university? What was he thinking about? Okay, I'll read that. Universities are rapidly developing into more than mere places of learning. They are becoming major economic influences in the nation's industrial life, affecting location of industry, population growth, and the character of communities. Universities are, in brief, a natural resource, just as raw materials, transportation, and climate. You can see he's an engineer. He's looking at it as raw materials. Whereas in most regions, they think of the university as the ivory tower. And so by the time he begins to look at the area as the raw materials and thinking about it engineering-wise, we begin to have this whole population that comes after that vision. And this is from the wellsprings of innovation that keeps track. And it looked at, in 2008, the Stanford affiliated companies on the top 100. It looked at, well, they were worth about $4.2 billion, and it moves and rises. But you can see that from that vision, the returns becomes quite an interesting set of values. That's the capital return. But later on, the next slide I'm going to show comes from a guy by the name of Ted Zola. Ted Zola wanted to understand the networks that were present in different regions of the country that wanted to emulate the Silicon Valley. So in terms of network, he has grabbed it. Here's Boston. That's the Silicon Valley, Denver. And now these are networks of people who are, he called them deal makers. They're really investors. Investors, by the time they invest in many companies, they're like polling bees. One looks at this map and thinks, well, Silicon Valley and Boston, they're both dense. The next slide will show there's a marked difference between the two ecologies. Okay, so again, deal maker, this is Silicon Valley. What this shows is that in the Valley, there are about 89 people who are sitting on the boards of 10 or more companies, actively making deals. There are 140 sitting on the boards of 9 or more companies. When you see that big jump across, you can begin to see part of what's making the valley what it is. That with this amount of cross-pollination and recombination going on, it gives us a sense of some of the mechanics by which the network dynamics of the valley. Most other regions, and you all know, I think most of you stay up very late. I think you're the ones causing this graph to go up. But there's another thing that is happening in the valley when you look at the role of venture capitalists. In some of our studies, I talked about the disposition variables. In over several years, when we've polled, most Stanford engineers and designers are introverts. About 80% of them are introverts. A lot of countries have money, but the monies are given to bankers. Bankers are like farmers. They don't go anywhere. But venture capitalists are like hunters. They move out. So you have this introverted population, but a hunting population that will come to Stanford, knock on my door. What do you have there? So by making, and what the venture capitalists were doing was that they were making capital mobile with their feet. A banker will say, oh, you have this idea, come and see me in the bank. An introvert to come and see you in the bank, a very, very tough chance. So the venture capitalists became very integral part because their disposition as hunters paired with the disposition of the engineers and designers who are introverts. And so it made it easier to have that blend between technology and capital. So I have a lot of regions in the world that they have money, but the money is sitting with people for whom money is power, power is status, and status means you have people come to meet you. So that capital is not mobile. Part of what Robert Solow was in his derivation was that it was the mobility that was causing some of the changes we had. One other element of the venture capitalists is that in general, they are much older than the entrepreneurs. Okay, so the next slide shows a very interesting variable here. This is what happens to our mind as we age. This is work by PARC and several people. Our processing capacity decreases. That's the speed of processing. Now you're all quiet. Okay, I have. Okay, but our world knowledge does increase. And so what you see when you look at the venture capitalists and the entrepreneurs interact is that knowledge is coming from here to pollinate here. In most other regions of the world, they only think of this graph. So young people are meant to be seen and not heard. They are not using their processing capacity. So in the valley, it's that when we bring the knowledge from the venture capital, because they have a trust network, they can have more access to capital, and they bring both that expertise to pollinate and help the young, magic happens. So as we begin to see these issues of that how things are beginning to happen, we can see how old traditions in different cultures could inhibit. It's not like, and we've almost discovered it by accident. One of my colleagues, Phil Wickham, he often says the Silicon Valley is populated by lonely, desperate people. So we network very much because most of us are away from our families. So we have a bit of extra time to network with other people. But one more thing. Even though we had all these variables, we still had a challenge. And the next slide I'm going to show comes from some of the work done by Victor Huang and Greg Horowitz. Victor is, I call him a designer. He doesn't know. He says he's a lawyer. I said, what's that? That's a lawmaker. That's a designer to you make laws. But he comes to the valley, he's looking around, and he starts to write down the rules of the valley. I said, why are you doing that? Well, he's a designer. They write down rules. That's what lawyers do. So Very interestingly, he came up with a set of rules because he has been in different parts of the country and said, well, looks like the rules that are operating in the valley are very different from the rules that are operating elsewhere. A caveat there, before I mention that, in the US system, we use, our system of law is the common law. In most of Europe, they use the civil law. So already they have one leg down, shall I say. Because the civil law says that if the rule in Paris is applied the same way all over the country. So civil law is an application law. But common law is an interpretative law. So the rule in Washington, D.C. may not obtain here in California. Because the judge may say, well, here's HP. The law says we should give it maximum of 20 years, but it's been helping the community, so we'll waive that a bit. That's what common law allows us to do. But in countries where it's civil law, the laws are not context dependent. And that would often stifle their innovation. So Victor comes and he says the rules here are very different, Victor and Greg. And so he was able to list what's the rules elsewhere in the country. He says there are rules of a place called the plantation. Excel at your job, be loyal to your team, work with those you can depend on, seek competitive edge, do the job right the first time, strive for perfection, and return favors. And he said, nothing wrong with these rules. They're perfectly good. Now let's look at what they came up with for the rules of the Silicon Valley. Break rules and dream. Open doors and listen. Trust and be trusted. Seek fairness, not advantage. Experiment and iterate together. Err, fail, and persist. And pay it forward. I'm just summarizing part of that work here because there's a lot more to it. But you can see the rules are good. Both rules are good. But they have different effects. If you put in this control law and put in this control law, you'll have different circuits. They'll behave very differently. So what was then, this was really beautiful. I just love this. Because a lot of people say, build a university and build a technology park. Those are just buildings. It's our behaviors that emerges the artifact. So this was very good. So as I looked at it, I said, okay, here is what a production system looks like. Households, universities, firm, and market. Everybody can do that. But as we studied this more, and this has only emerged, that's why I said work in progress. So the next slide I'm going to show you is work in progress, okay? What I thought was really happening was that in the, so the economy in Europe has stagnated a lot, and I was there in January and was talking with them. And it occurred to me that this economic model of the government was not perhaps right in the US. This is not what the model looks like in the US. That if we had to model our economy, we have a double loop. Because this could be the rest of America. But you saw the graph where Silicon Valley went off scale, that there is an outer loop that is going on in Silicon Valley where we have this whole startup economy, ecology, and for a long time we also had a secondary market. The secondary market is like the defense industry. Because if you remember, when Intel came out, the defense industry made a big order. If you can have these secondary markets make a big order, your learning rate in the company shortens very much. But what I'm proposing here is that based on the Rainforest book, we actually have two economic systems in the country. And that what California has done has been something very interesting. Greg Horowitz, who I've been talking with, he said, Adi, I think it's that there's a pulse. You should measure the pulse. So I said, what's the pulse? And as we discussed, I began to understand what he was seeing in the valley. So pay attention. Let's see how the US economy works with California. Now, before I do that, I should tell you one joke I had. So during the Iraq war, there were two young boys talking. And one young boy, the first one was not for the war. And it was on a commercial and said, well, you're not for the war. Either you are unpatriotic or you're from California. So there's something there. But for all what I've said, I hope you are seeing that it's not specific to California. It's just what are the conditions that makes California or the Silicon Valley possible. The age differences, the networking. And these are things that I believe other regions can copy. So let's see how the Silicon Valley works. In that pulsing, it's pulling the rest of the country along. Now, that pulsing it's unstable. And a lot of cultures like stability. They'll quickly make it rigid. These are layoffs. Because when a layoff occurs, people disperse, but they take the knowledge to the next company. Most countries have laws against laying off. So the knowledge is not spreading. And several of you in this room have experienced this firsthand. You got laid off, and you have to find another company. You are part of that pulsating economy. And as we pulse, the economy begins to move around. Okay, so that's what we're beginning to see. And we're looking at some data. The federal government, for a long time, wasn't keeping a lot of the jobs data. Part of the pulsing is also the migration, the labor movements that you begin to see. So we're now tying our own interaction amongst ourselves, which you saw happens in our lab, but how does it scale up? And it's this pulsing that becomes really very fascinating as you look at the larger economy. So what is the implication in terms of science and academic? Several years ago, I sat in when the dean of the School of Engineering at Stanford was describing the rationale for having bioengineering. This was about 12 years ago. And here is what he said. I'll have to read it for the people. Sorry, okay. Biology and medicine have historically been qualitative sciences, but that is changing. We now understand the molecular basis of living systems. We can measure biological systems at the molecular level. We can develop models of how living systems behave. We can design molecules and create new drugs. Biology is thus becoming a more quantitative science like physics, chemistry, and mathematics. Biology is ready to become a new foundational science of engineering. The question before us is, can we say the same for design? So I wrote the same thing, similar. Design, the process of artifact creation, has historically been a qualitative art, but that has changed. We now understand the cognitive and communication basis of artifact creation and diffusion. We can measure artifact creation at the human interaction level. We can measure artifact diffusion at the economic and environmental level. We can model artifact creation behaviors. We can design new behaviors to produce innovative outcome with greater certainty. I would argue that design thinking has become a more quantitative science, like physics, chemistry, and biology, and that design is ready to become a foundational science for engineering. Thank you. One of the people who has influenced me before I take questions is my wife. I see her in the audience. Thank you very much. Are you going to stand up? Okay, please, I told you it's a conversation, so ask any questions. There are a number of people who I mentioned are here. Victor is here, Sharik is there, so I have enough people to answer. Okay. Yes, please. I think, okay. Remember, designers ask questions, so please ask lots of questions. But really, the questions, if I can't answer, I'll ask anybody that can answer it here in the audience.
Thank you very much.
You're welcome.
One of the things that may be confusing here, you're not seeing because you're not old enough.
That's why I said there are a few older guys in the room that can answer.
When I was an undergraduate, the focus of science was shifting from innovation from people who knew how to do scientific development to people who were measuring using true-false questions. True-false questions are not the way to design anything. They don't work. What was critical is that 55 years ago, if your work involved asking true-false questions, you couldn't get tenure.
Aha.
No, pardon me, 65 years ago, you would not get tenure. You would be thrown out as a hack. 55 years ago was the tipping point, and 50 years ago, you could actually get tenure by asking those kinds of questions.
The generative ones.
The true-false questions.
Okay.
Does it work, does it not? Does it work, does it not? And the problem, the real problem, is that if you look at a design problem and you ask, does it work, does it not, your ability to converge to a solution is about 1%. Whereas if you're asking questions like, what do I have to know? What do I have to know? What do I have to know? What's the next step? What's the next step? What's the next step? You can typically converge to a solution in 5 to 7 iterations 85% of the time. I had the honor as an undergraduate to be working with people who still knew how to do this.
Very, very true. Yeah.
So that's how far back it went.
Yes.
Because my bachelor's degree comes from 1962.
Okay. Yes. I totally agree with you. So those are the generative design questions that we want to encourage more people to answer.
Hi. So beginning of the presentation, you said work in progress.
Yes.
So what kind of work you really want to accomplish and what it would look like in your dream? The next question, what do you really want to be known by?
What do I want?
What do you really want to be known by?
Okay. So the question was, what will this look like?
What's the dream?
You know, I think, so there's the way I would answer that is that as an engineer, we do a lot of our work collaboratively. And this is just, for me, the beginning, that these are a few measures of how we can do design. There's just a lot more work to be done. There's a lot of, the measures are presented, we've not yet calibrated them. We have to develop that measurement system. So there's a lot of work in terms of just cleaning it up and getting it ready to work. For us, it's that flexibility in, I love to create things as an engineer. And for different problems, I like to say, okay, what can we use to solve that? So one of the things we're doing now is that we have a center in Ahmedabad in India and one in Nigeria, where we have taken part of the curriculum from Stanford, but also I'm working with a few venture capitalists to nucleate a Silicon Valley in each of those environments. India, for example, I think has about 38 states. Now, each of those states is a country. You know, so a lot of people say, oh, we have Bangalore. I said, Bangalore, yeah, it's, that whole area is just one country. So we can have many Silicon Valleys in India. So we're right now in Ahmedabad, where we're trying to foster collaboration between the different parties so that, so creating a Silicon Valley equivalent. Remember, I said, Silicon Valley for me is like a steam engine. Those are the properties, and so we're in regions where there is high youth unemployment. We know they have high processing capacity, and the internet now distributes knowledge. So the knowledge that we can, so it's been now to, I think if you ask what am I currently working on, it's really on the mechanism of the variable of capital. Because it's not, a lot of people get stuck with capital is money, but capital is just a signal. So if you can get that signal to feedback, you will find that, I mean, it's an incentive system. So a lot of places have broken or noisy capital signals. If we can clean up the capital signals, which I think we can do through some of the virtual currencies, Bitcoins and XRP, then we can, in fact, stimulate growth in this region. So I would say the stimulation of economic growth and well-being for people is what I am quite interested in. Yeah. Oh, sorry. Yeah.
I notice you said nothing about overspecialization. We start out as humans hunting and gathering where we have only two specialties, father, mother. Children don't count. Gradually, they move into one of the two specialties. Today, we produce such narrow specialists that they're totally ignorant of the process to identify where similar solutions have already been implemented in other industries. So, as a society, we need a process to educate and certify people who can do what the biographers claim Steve Jobs did, only hopefully with a better attitude toward people.
That's a very important problem, the over-specialization, and most of you will see it particularly acute in the medical field, where over time, those that were specialists got more of the money, and we have not too many general practitioners.
There's a gentleman right here, right there.
I defer to my mentor from the Clean Tech Open. Go, sir.
What's that?
No, he's...
Oh, your mentor, okay.
Everybody's mentor, actually.
What do you see as the relationship between design thinking and a business model, in particular a disruptive business model?
So the business, I don't quite understand between, yeah.
You know, you have to, if you've got a disruptive technology, you need to develop a disruptive business model.
Yes.
What is the relationship between that process and design thinking? Have you looked at that?
No, I haven't looked at that. I'm kind of trying to think on my feet because a lot of the the closer disruption that occurs to me is that startup companies are basically disruptive to the big companies. And so when I have, and if you combine startup companies with venture capital, then you get a disruption. So just as an example, Microsoft has its Bing. Google comes. Now, but Bing, the allocation of funds to Bing within Microsoft is constrained by the funds in Microsoft. So they allocate $5 million to Bing. But the venture capitalist gives Google, a smaller company, $10 million. Then even though Microsoft is a big company, for that particular unit, Google can take it out. So that's how I look at disruption, that the venture capitalists just allowed us to amplify some of the very smaller companies to cause disruption to the bigger ones. So that's how I kind of look
Venture capitalists are not necessarily experts in building a disruptive business model.
No, the entrepreneurs do that, but they supply the resources to challenge the incumbent.
I'll talk to you afterwards.
Okay.
So I confess I'm a subversive. I snuck in the room.
Okay.
I'm an architect. Shh. So architects, we by and large are ego designers, not eco designers. And we're happy to do that.
Yes.
Until we get caught. Well, here's the thing. It might be helpful to distinguish design as a verb from design as a noun.
Okay.
I wonder if you might want to talk about that a little bit.
It's a very good question you've asked. We have a course at Stanford that teaches the architecture, engineering, and construction industry. And they have been moving towards increasing more collaboration
Integrated project delivery, for instance. Yeah.
So part of, and you are very correct that for a lot of architects, and sometimes for the designers, it's really about ego design. And that's the name of the game. I wouldn't be able to say much about ego design, but I can, because most of our focus has been really on the collaboration side of design.
I understand. So let's negotiate here a little bit. So what we do,
happy to.
what we do, and I believe there was a gentleman who used the term before, we dream. We dream. And we also profess to design the truth. So I think what you're talking about is searching for what really is the truth beyond the limitations of the truth that we currently are toiling under. Searching for a broader sense of what is the truth with regard to the entire human condition around the globe and out into space.
Yeah, I will grant you that. I think the aspect of dreaming is really very important in terms of how we come up with ideas. The point you raised about people that design alone, part of it is also looking at what's the complexity of the problem they're addressing. So there's a limit to what the individual can do. And so the team is what increases that ability to manage a larger complexity.
Hi. So I wanted to ask you a question. So you mentioned that you have a incubation center in Ahmedabad, India.
Yes.
So now India has primarily socialist policies as a state. And I was wondering if that is a function of how design thinking works. Because primarily, I believe, a capitalist system is very important to incubate design thinking. Citing Fountainhead, we have seen, so yeah, that's primarily my question.
Okay. So just to mention, like I showed you the pulsating, if we made the whole of the US California, it won't work. Yeah. In fact, we do rely on some of the Midwest. They are able to do a lot of the mass production. We also rely on Taiwan and Asia to do some of our production. So there's a sense in which this pulsating, it's a small section of the fraction of the population, but it's enough to begin to drive the other. So we are in Ahmedabad. Ahmedabad, where we are, has the top business school in India. It has the top design school in India, and it has a second-tier engineering school. But they don't talk to each other. Because within each of these fields, going to your point of ego, the management people feel, why should I talk to these engineers and designers? The designers feel, have nothing to do with you. But you can see, and I tell them that the dysfunction of teams, an economy like the US, we can bear that dysfunction because we are big enough. We have enough momentum. But for a lot of developing countries, the dysfunction of status and ego, where a lot is suffering in society, is something that it's not, it's almost like you can't take that, it's a luxury that can't be afforded. So we're looking at ways to get people to collaborate. But just to mention one point about that, it's not easy. Getting collaboration in India and a lot of developing countries is very difficult because for a lot of those countries, I come originally from Nigeria, and I was asking people about what's the pattern of leadership in India? What's the pattern of leadership in Nigeria? And because it was during the last election, and people called Modi a lion. So I said, if he's a lion, are we cubs? And they said, no, he's just a lion. So I said, okay. Because within the Judeo-Christian system, for example, there's the good shepherd and the sheep. And so the model of leadership is defined within that metaphor. And so I probed around, and somebody responded and said, in India and Hinduism, it came out of a more peasant society. And peasant societies tend to be more fragmented because each person had their own farms. And so the collaboration that we'll see in some of the congregational religions is not there. The infrastructure is not there. So we have to sort of build that in. Yeah.
So you have... So you have a very nice language for describing the interaction among engineers, and you showed some examples. How do you apply design thinking to that, to know that where's the feedback loop so you can verify how correct your model is, how well it describes things, how completely it describes things?
So I mentioned that it's actually reflective and reflexive. So the teams we work with, they get to see the feedback on their process. So they're the ones really commenting. We're more or less facilitating their process of reflection.
The meta language, how do you improve your description of the process they're doing?
That's a good. So two ways we're doing it. We are, which is about calibrating it. Yes. Okay. So we're calibrating it both within known design systems so that we know what the answer is, so we can calibrate it. But we're also calibrating it across cultures so that the cultures can check on each other. And so that's one of the ways that we've been calibrating it. Now, ideally, what we'd like to have, and this is something, we'd like to have a design Olympics. Because what the Olympics does, it's a comparative way where we're able to see where is the leading edge. And one of the videos I was going to show that captures some of what I think was in 1968, a guy by the name of Dick Fosbury. He was competing in the Olympics, and he jumped with the back of his head over, and that was the first time somebody did that. And I thought, wow. But once he did that, every other jumper, high jumper, repeated what Fosbury did, because it turns out that his center of gravity actually goes below the bar. So as we study design, what I'm hoping we'll find is that new ways of thinking that we've never seen before, because we've never recorded how we think as humans. But once we see a particular way of thinking, we can copy it. We're fantastic imitators as humans. So this representation is to also enable us to discover the outliers. And because once we know the outliers, how do you do that? So an Olympics is an event that showcases human abilities. So by having that human abilities show up in new places, we hope we will be able to both make the discovery, but also share it with a wider audience.
So we have time for 3 more questions. One right there, one right here, and...
You're all doing very well, asking questions. I love that.
Well, you already had an opportunity to ask a question, so someone who hasn't had an opportunity to ask a question. So I believe that gentleman back there wins.
Okay. Thank you so much for a really engaging presentation. I felt like I was learning throughout the whole time and really excited. So you talk about how design thinking has basically matured to the point where it's ready to be a science, and that's a good thing. 2 questions based on that. 1, what other fields do you think are about to mature into sciences? And 2, what other fields do you think are about to mature into sciences? And 2, what fields do you think will yield the most benefit to the human condition if we mature them into sciences?
Okay, that's a good question. In terms of the maturing into sciences, for me, design becomes really the obvious one. Because for a long time we had had this schism between art and science, and we got caught into that. But when you look at what engineers and designers do, it is very primordial of what humans do. Apart from studying the teams, I also take an interest in studying ants and spiders. They also do design. Ant hills are fantastic designs. They communicate chemically, the ants. Spiders, when you look at the different things they've done, but they don't have language, and most of them, they're not mobile. So there's a lot that I think we will gain by really beginning to understand that as designers, we're doing something very much like the ants. We're building these structures using the environment and using our ingenuity. But we can innovate, I think, because we make mistakes. If we didn't make mistakes, I don't think we'll innovate. Those ants, I've watched them, they don't make mistakes. They just so part of our mistakes and the ability to recognize the mistakes becomes very critical to our evolution. So I haven't looked at, I've sort of, some people come, and tell me, why don't you come and study all scientists? I said, no, I'm an engineer. I kind of work with engineers and designers. And so if any field wants to evolve itself, it can engage in a reflective and reflexive process to understand it. Now, even after I've said this, there's still a lot of battles to be fought both in different universities, because for a long time, universities thought of design, that it wasn't part of engineering. And we've just said it is, and that's what engineers do and designers do fundamentally. So there's still a lot of battle to be fought.
Thank you very much. So I'm very interested in this whole concept of specialization, but what I think is an opportunity is the cross-pollinators, right? So what are the bees that are going to go between these various roots and trees? And so I'm wondering if you can think about, is there a design element there? And next, the cognitive narratology, fascinating. What kind of pickup is that getting? Where do you see that going? Or is it sort of confined to a group of academics? And what can we do to get that out there more?
So the cognitive narratology, I think part of that work, I don't know if you know the work of Hofstadter, who says really a lot of our communication is through metaphors. And so when we had started using it, what we used it for initially before was by understanding the metaphors across culture, we could increase intercultural communication. Because when people are talking, you can begin to see the metaphors they hold in their head. So we feel in this era of globalization that understanding these underlying metaphors will be quite an interesting way in which we can engage with ourselves. Hopefully, it will also reduce conflict. This afternoon, I was talking to Mark Nelson, who has championed the Peace Innovation Lab at Stanford. And they are saying that can we make peace for profit? When you look at how much is lost in war, then profitable peace becomes a useful alternative. So I think this notion of designing peace, because conflict is not too difficult to provoke conflict. So we are hoping that we can begin to have more peace and prosperity. So that's how I would put it.
One last question.
So your comments on diversity in collaboration, you talked about in India, the different schools.
Yes.
What is surprising from a diversity overall and the impact of cultural diversity that you see in Silicon Valley, and how does it foster innovation and design thinking?
Aha, that's an interesting one. I too have wondered myself, how did Silicon Valley discover, how is it able to cope with the diversity? I think we have about 40% of non-native born people in the state. I've heard of two hypotheses. The first, which was written out in the book on rainforest, is that Silicon Valley developed out of the frontier culture. And so we are still vestiges of that frontier culture. So in the frontier, you had to have rugged individuals who depended on each other for survival. So even if I don't like you, it won't be smart to kill you because you have to protect me. So we, in a sense, necessity forced collaboration on us because of that frontier culture. And so we've still preserved some of that frontier. You'll see some of that frontier culture in ages past in Pittsburgh. Then it became settled. And once people get settled, they're no longer pulsing. Because, I mean, pulsing is a bit difficult. Silicon Valley has managed to keep pulsating. And also the good weather has also attracted people. The second element of, if it's not the frontier culture, the other culture that I think could also have contributed was the drug culture. Okay, because with the drugs in the 60s and 70s, they lower inhibition. And when our inhibitions are lowered, we would interact more with some cultural diversity. Now, I'm not recommending. I'm not recommending. But we do know that alcohol and drugs has the effect of just having people chill and just being cool. So I think those two things. Now, the state I'm operating in India is an alcohol-free state. So we're trying to see, can we adjust the policy? If we want more innovation, we will have to allow a bit more alcohol, but we don't know. But it's just that as humans, how do we just chill? Because for some of the innovation, we need some of the relaxation techniques. So one thing we've been exploring is whether we could get, I mean, while we're in India, can we use some of the practices of yoga to get people to blend? We don't yet know, but it's looking at what could come out of the culture.